Hello and welcome to this video looking at the classification of stars. In your previous lesson we will have already looked at this diagram called the Hertzsprung-Russell diagram. You should already be familiar with many of the types of stars that we have on this diagram. We have our main belt through the middle with our main sequence stars, and this is where the Sun would be found, at around about 6,000 degrees Kelvin, so in around here. We then have our red giants and also our super red giants, and on here additionally are our white dwarfs. You'll also remember the scale, so we have our temperature scale, which actually works in a counterintuitive way compared to normal graphs, in that the temperature is going down as we move across the x-axis. And then we have our luminosity scale on the y-axis. You'll notice on this diagram that as the temperature changes, the colours of the star also change. And you should remember this from our studies of the evolution of stars. We're now going to take a closer look at why we see these different colours, and then use these ideas to help us classify our different types of star beyond their phase. So, to do this, we need to think a little bit about black body radiators. Stars are always described as black bodies, and this means that all of the radiation incident on them is absorbed and isn't reflected. The consequence of this is that when we look at the absorption or emission spectrum from one of these black body objects, we see the full range of the electromagnetic spectrum, and we don't see, like with a discharge tube with a particular gas filled inside it, particular wavelengths coming out. However, depending on the temperature of the object, as you can see by the different curves that we have on this graph here, what we can see is that we have a greater intensity of light which is emitted from particular wavelengths. This means that each of these black body objects will appear a slightly different colour, due to the wavelengths that they are emitting. Interestingly, we have an inverse relationship between the temperature and the wavelength. So as my temperature increases, we actually see that the maximum wavelength or maximum intensity wavelength along here is actually getting smaller. Wien's law is then a law to explain this relationship and to give us a numerical calculation that we can complete in order to find the maximum wavelength and therefore identify the colour of the star. Wien's law tells us that the maximum wavelength, my lambda max here, times by the temperature, which should always be in Kelvin, is always equal to this constant, 0.0029. We should note here that this unit is actually metre Kelvin and not millikelvin. So, by measuring the maximum or peak wavelength from a particular star, we can very, very clearly and quickly identify its temperature. This temperature is the absolute temperature of the photosphere. The photosphere is the light-emitting outer layer, or sometimes referred to as the surface of the star. We can't actually directly detect anything about the temperature of the inner core of the star, but we can then infer some of this information from the outside temperature. So we've now linked the colour of the star directly to its temperature, and this allows us to start classifying our stars more precisely. Here is a slide from your course notes which can be found on Edmodo. We're going to have a look now at the spectral classes, and you'll notice that our spectral classes are down the left-hand side of the column here. They go from O, B, A, F, G, K and to M. Now this might seem like a very bizarre order to these spectral classes, but initially they were ordered in alphabetical order due to the colour that the stars appear. After this, it was then realised that actually a better way to order these stars was using their surface temperature, and this has then meant that the spectral classes and the classification order now seems a little bit weird. You can see though that our highest spectral class, the O class, has the greatest temperature from 25,000 to 50,000 Kelvin, whilst our M-class star at the bottom, which is a red colour, has the lowest temperature, which is approximately 2,500 to 3,500 Kelvin, so a much colder star comparatively. The colours also allow us to have a look at the absorption spectra, and we do see some specific absorption lines for each of these stars, which is representative of the types of materials that might be present within the stars themselves. So, for the O-class star, these are very hot and bright, and we can clearly see from our spectral lines here that mostly we have some helium, some ionized helium and some hydrogen in these stars. Conversely, as we go down through the classification and the stars become much cooler, we end up with some of these heavier elements that we can see as absorption lines in here. These red and orange stars are normally stars which have gone through their main sequence and now are in their giant or super red giant phases. This means that as a star they have gone through many of the processes of fusion and so have been able to produce some of these heavier atoms. It should be noted here that the absorption spectra that we're viewing in these diagrams is from the corona of the star. Now this is the hot gaseous area which surrounds the star, so it's above the photosphere, above the surface of the star. These absorption lines are indicative of the types of atoms that can be found outside of the star. And these spectral lines that we see here can then allow us to classify the stars even without calculating their temperature directly and looking at their overall colour and blackbody radiation pattern. The information in both this table and for the spectral classes with the absorption spectra is really important for your exam, and you can be tested on this for factual recall. So I would strongly recommend now that you take a note of this table and the prominent absorption lines. This can be just in a written form as in my table up here, because this is information that you will have to learn for next year. You might want to pause the video now to do this. We're going to extend our understanding of this classification of stars using the Balmer series next lesson, and we're also going to begin looking at how to calculate the power of stars and their magnitudes.